So we have made it to the last video on probability. We're still in continuous variables. Let's look at the map. Here we are. And we've already done normal distribution. What we're going to do is combine all three of these into one video, which is not going to necessarily make it a really long video because we're just going to be doing an overview of all of these, not going into nearly as much detail yet. They will come back. In fact, all of these are going to be part of inferential statistics, which is going to be very fun. Can't wait to get there. But that's why it's going to be t-distribution, chi-squared is how that's pronounced, and f-distributions, an overview. What we're going to do is just a little compare and contrast of the different distributions. They're used for different things, different questions. So we just need to make sure to know when which is used. The normal distribution, which we've already studied, is used with a known population ideally. Oftentimes we say that it's approximately normal and that that's good enough. But ideally, we would know the whole population. If you remember the lizard or the iguana example, that we know the parameters, which is the actual mean of the population and standard deviation of the population. We know the shape of the normal distribution. All right. Symmetric, about the mean. We have our standard deviation. Everything's pretty familiar. And of course, it's mound-shaped and symmetric. Now for the t-distribution, let's start by looking at another page. So here is our normal distribution that we're familiar with. Now the t-distribution looks a lot like the normal distribution, doesn't it? It is a different shape, though, mostly. And here, over here, is a nice comparison. What I'll do is I'll highlight the normal distribution. There it is in blue. And these other ones are the t-distributions. So the shape of the t-distribution is mound-shaped and symmetric, but generally it's a little wider. There's more variation. Standard deviation is generally a little bit bigger with the t-distribution. And unlike normal distribution, there are many different t-distributions. There's only one normal distribution. That doesn't ever change. But we have different t-distributions for what's called degrees of freedom. And the other distributions have this similar concept of degrees of freedom, which we're going to need to go over, and maybe we can do that right now. So in trying to figure out this idea of degrees of freedom, looking at it in this table, or using this table, I find fairly helpful. So we're looking at data sets and how many elements there are in the data set. We can start off with the smallest data set, really. There's only one number in the data set. Then maybe we could go and increase it to 2 numbers in the data set, or maybe 3 numbers in the data set. We want sort of a target average for the data. Right? So let's just somewhat arbitrarily say, for each of these, we want the numbers to average out to be 10. Now, here comes the important part. Because now we get to make example sets. Say, all right, well, let's make up a set of numbers that has that average of 10. And it has to have this number of numbers. That's essentially n. So we only have one number in our set. The average has to be 10. So guess what? 10. Did we have much freedom in choosing this number? No. We didn't have any freedom at all in choosing that number. It had to be 10. So down here, how many numbers were we free to choose? We weren't free to choose any numbers. That number had to be 10. We had no choice. But if we come over here and say, well, we have two numbers now. Could we choose this number to be, I don't know, 2? Sure. Once we have made that choice, can we choose what the second number is? Or is that second number now set? Right, it's set. We don't have any freedom in this number. It has to be 18. 18 and 2 is 20, divided by 2 is 10. That's our average. If we wanted to do another one, could we have chosen the first number to be 5? Sure, we could have chosen that. Can we choose a second number? Nope, has to be 15. So in the data set, how many numbers were we free to choose? We were able to choose one of them. Once we chose that, the other one had to be set. We had no choice. If we had 3 numbers in our data set, we could choose maybe that to be 0. We could maybe choose this to be 5. Could we choose this number? No. Again, it's the same idea. Has to be set. That ends up being 25. So how many numbers were we free to choose? 2. All right. There's a relationship between the number in the data set, n, and this is called the degree of freedom. So if we have n elements in the data set, degrees of freedom, n minus 1. And that's how you calculate degrees of freedom for the t-distribution. Now, other distributions for other scenarios can sometimes get more complicated than this, but that's a good introduction to degrees of freedom. So now looking back at our t-distributions, now that we know what degrees of freedom refer to, and really, degrees of freedom is talking about how big the data set is. And to anticipate where this is going, really the vocabulary word is sample. Right? How big is your sample? Right? Your measurements is your data set, and if you have only 2 measurements, your sample size is, in this case, 3, because n minus 1 is your degrees of freedom. So this has 3 elements in it, is down here. And what happens as the sample size gets bigger, the degrees of freedom go up. It's getting closer and closer to the normal distribution. And that's actually very important, because at some point in time, the difference between the t-distribution and the normal distribution more or less goes away. It's never exactly the same, but it's so close that we could actually use the normal distribution for sufficiently large samples, because really the distributions are just about the same. So now, going back to our summary page, we know that the t-distribution looks a lot like the normal distribution, although typically it's wider, right? Centered around the mean. The question, and we know that it has that degrees of freedom, which refers to sample size. So t-distributions are used for samples, and especially small samples, because as I showed, big samples, the t-distribution actually gets indistinguishable from the normal distribution. So samples, and primarily small samples for the t-distributions. Besides that, it's actually used in the same way and for the same thing as the normal distribution. But for samples, which means I need to make a change. I use the population parameter symbol up here, which of course I shouldn't have. This is a sample mean. So when you take a sample, right, you measure the height of 20 people, you get a sample mean. If you measure the height of 20 other people, it might be a little bit different. There's always going to be variation between samples, and this describes that variation of sample means. This is the whole population, which you would also find, and let me write this out. There's standard deviation, variation of the whole population, and sample standard deviation, variation within the sample. I'm not sure. I might have said that this is the variation of sample means. If I did, I was mistaken. That's actually thinking ahead to inferential statistics. These are actually the individual measurements within the sample. Right? There's an average of all the measurements, but the measurements themselves in the sample have variation around that average. So just want to clarify that. Now, going on to chi-squared. This is Greek letter chi, which is how you write that, more or less. Let's go back to our this page, probability distributions, and let's scroll down. Now, down here is the shape of the chi-squared probability distribution. Chi-squared also has the degrees of freedom concept, df, and unlike the t-distribution, as the degrees of freedom increases, it gets taller and narrower and gets closer to the normal distribution. For the chi-squared distribution, as the degrees of freedom increase, you can see that this has a really right-skewed shape. As the degrees of freedom increase, the maximum reduces, and so does the right-skewedness. It becomes more symmetric. It's no longer the bell-shaped kind of curve. It's actually a very different kind of shape. So let's write that up in our summary page. I've tried to draw the right-skewed chi-squared distribution. Now, what is it used for? It's actually a really interesting distribution. Used to judge whether observations match expectations. The distance or the difference between observation and expected value, observed or measured value, and expected value. So you subtract them. It's a little bit more complicated than that, but that's the underlying idea behind chi-squared distribution is do things match? And that can actually play out in a couple of different ways, which I can list off for you. They're called goodness of fit, which is a funny term. But if you have, for example, an equation, which is a model that you've come up with trying to predict whatever you're trying to predict, well, it'll never be exact because there's always variation. Well, how good is the fit because of the model, or is it just random? And for homogeneity of population, are the subgroups within a population really the same or not? Again, it's that concept of observation versus expectation. If we expect them to be the same, are they the same? And we can even apply it to two variables to figure out is there an association between those two variables, or are they really independent of each other and there's no association? It all comes down to this kind of concept of observed versus expected, measured versus expected, or modeled. And that's going to actually spend a lot of time on that one. All right, for the F distribution, let's go back to this page and scroll down. And so here we have our chi-squared that we talked about over here. And down here we have the F distribution, which is also a right-skewed distribution. I don't have any cool little comparisons for the F distribution. So let's go back to the summary page. Get some description written up. Here's my attempt at the F distribution. It is used for the analysis of variance. And you'll notice I've done some funny capitalization here because the short form of analysis of variance is ANOVA, which of course you can see ANOVA. That's where the ANOVA comes from, analysis of variance. So as it sounds, used to judge whether the spread of a population has changed or not. There's, again, this is getting a little deeper perhaps, but we talk about means over here. We can actually talk about proportions also, and same with chi-squared. This is actually the first type of analysis where it's actually focusing on standard deviation, right? Measures of spread or variance, which is why it's ANOVA. Now, with all of these, we have the distribution statistic, it's called. We already know one of them. We've already worked with it. Maybe I will go in a different color. Right here in the normal distribution, if we wanted this area, of course, what statistic are we working with? That would be z-score. Well, these other distributions have the same kind of concept. This, of course, would be the t statistic, which functions very much like z. And over here, we have, of course, the chi-squared statistic. And over here, we have the F statistic. Really, all of them functioning very much the same. It's the position on the axis. So that's actually about all that we're going to get into with these other three distributions for the moment. If you remember, I mean, the video on the normal distribution, that was, I think, over 30 minutes. We have at least that much, if not more, on each of these, really. And at this stage, what I'm most interested in you kind of holding on to, right, is just get what they're used for. We don't know how to actually do it yet. That's going to come later. But I would like you to know that's used, chi-squared is all about the difference between observations and expectations. F distribution is ANOVA. You should actually probably recognize ANOVA as the F distribution. And that it's about spread. I mean, that's what the F distribution is all about. T distribution is for samples. And if you know that, that's good for the moment. I think I forgot to put these right skewed on earlier. Just want to draw your attention to the fact that I did put those down. And that's also something that you should know, right? You should know the basic shape of each distribution, and you should also know about degrees of freedom. That's really what I'm wanting you to know for the moment. And again, there's going to be a lot more detail about these distributions later. Oh, and I almost forgot the calculator. I just wanted to draw your attention. If you go into the distribution menu, right, we actually now have a better understanding of almost everything in here. We have your normal PDF, normal CDF, inverse normal. I should show you that at some point in time. It'll come up in some examples, I think. Inverse T we haven't gone over quite yet, but again, that's going to be a T distribution thing. But here we have T PDF, T CDF. Well, that's for the T distribution. We have chi-squared PDF, chi-squared CDF. And we have F PDF and F CDF. So they're going to be very useful. We actually now know almost all of these in this entire menu, which of course is very exciting. So those will come later. I'm not going to show you the syntax of those yet. When we actually get into these distributions, I'll show you then, but I want to kind of seed this idea first.